Hello! In this lesson, we'll explore linear regression using the powerful language of matrix algebra. We start with a familiar equation for a line, which is our hypothesis function. Here theta 0 is the y-intercept, and theta 1 is the slope. Our goal is to find the values of theta 0 and theta 1 that create the best fitting line for our data. Now, imagine we have a data set with m training examples. For each example, we have a feature x and a target value y. This means we have a system of m equations. Writing out all these equations is tedious and inefficient. This is where matrices come to the rescue. We can represent this entire system of equations compactly using matrices and vectors. First, we group all our target values, the y's, into a single column vector. Next, we define our parameter vector, theta, which holds the coefficients we want to find. Finally, we construct the feature matrix, x. This is the clever part. To account for the intercept term theta 0, we add a column of 1s. This is like giving each data point a new feature, x0, which is always equal to 1. With these components, our entire system of equations simplifies to one elegant matrix equation, y equals x times theta. Now let's define our objective. We want to find the theta that minimizes the error between our predictions and the actual values. We use the sum of squared errors cost function j of theta. It measures the average squared difference between predictions and actuals. In matrix form, our vector of predictions is x times theta. The vector of errors is the predictions minus the actual y values. A sum of squared errors is equivalent to the dot product of the error vector with itself, which is written as the transpose of the vector multiplied by the vector. So our final cost function in matrix form is this compact and powerful expression. Our goal is to find the vector theta that minimizes this cost function. We do this by taking the derivative with respect to theta and setting it to 0. First, let's expand the expression inside the cost function. We start with the transpose term. Using the transpose rule, A minus B transpose equals A transpose minus B transpose. We distribute the transpose. Next, we use another transpose rule. AB transpose equals B transpose A transpose. Now we multiply the terms out, like using FOIL in algebra. First, outer, inner, last. Let's focus on the two middle terms. A key insight is that these terms are actually identical. Consider the term y transpose x theta. Since the result of these matrix multiplications is a single number, a scalar, its transpose is equal to itself. So let's take its transpose. Using the rule ADC transpose equals C transpose B transpose A transpose, we get theta transpose X transpose Y. Since the term is a scalar, it's equal to its transpose. This means the two middle terms are the same. So we can combine them into a single term. Now we're ready to take the gradient of j with respect to theta. We'll use a few standard matrix calculus rules. The derivative of the first term, a quadratic form, is 2 times x transposed x times theta. The derivative of the second linear term is just the constant vector part. And the derivative of the last term, which doesn't contain theta, is 0. Simplifying this expression, the 2's cancel out. To find the minimum, we set the gradient to 0. Finally, to solve for theta, we multiply by the inverse of x transpose x. This gives us the famous normal equation. Let's make this concrete with an example. Suppose we have 3 data points, 1, 2, 2, 3, and 3, 5. First, we construct our x and y matrices. We need to calculate x transpose x. And we also need x transpose y. Now we plug these into the normal equation. Theta equals the inverse of x transpose x times x transpose y. First, we find the inverse of the 2 by 2 matrix. Now we multiply this inverse by the x transpose y vector. This gives us our final values for theta 0 and theta 1. So we have derived the normal equation, which gives us a direct analytical solution for the parameters of a linear regression model. This method is very powerful because it solves for theta in one step, without needing to choose a learning rate or iterate like in gradient descent. However, it has a major drawback. Calculating the inverse of x transpose x is computationally expensive. If you have n features, the complexity is roughly on the order of n cubed. For thousands of features, this becomes very slow. For this reason, gradient descent is often preferred for very large datasets, while the normal equation is excellent for smaller datasets and for its theoretical importance. Thank you for watching.